Hey everybody, this is Dr. Jacobs and welcome to this week's lecture on distributions. It's all in the shape. So let's go ahead and get started. The unit learning objectives that I have for you this week are the following. I want you to be able to successfully create an ungrouped, cumulative, or group frequency distribution table based on the characteristics of the data set and the purpose of the table. I want you to be able to carefully create class intervals through identifying a practical class interval width that spans the proper number of class intervals for the data set. I want you to be able to follow the steps to create a histogram that accurately represents the data set. I also want you to be able to calculate percentile points and percentile ranks accurately. I want you to be able to explain and identify the various types of kurtosis, for example, platykurtic, leptokurtic, and mesokurtic. There we go. I also want you to be able to explain and identify the different types of skew. So there's going to be two types that we're going to learn about. We're going to learn about positive skew and negative skew. I want you to be able to identify the most common distribution shapes, for example, normal distribution, J-shaped distribution, U-shaped distribution, bimodal distribution, and a rectangular distribution. All right, so let's get started. So measures of shape, these are types of descriptive statistics that describe the shape of the distribution in one or a few numbers. So at this point, after this week, we'll have learned all the different branches of descriptive statistics that I'm going to teach you. We started out with learning measures of central tendency, where we learned about mean, median, mode. Then we learned about measures of variability, where we learned about exclusive range, inclusive range, mean absolute deviation, variance, and standard deviation. And now we're moving into measures of shape, where we're going to learn about skew and kurtosis. And so when we define the branch of descriptive statistics known as measures of shape, again, that describes the shape of the distribution in one or a few numbers. So we really need to define what distribution means then. And so distribution is a little bit of an abstract idea. And so sometimes it's a little difficult for students to understand what it means. But when we talk about the distribution of our data set, all we're talking about is how frequently each value appears within our data set. So if I asked 5 people, how many dogs do you have? The first person says, I have 0 dogs. The second person says, I have 0 dogs. The third person said they had 1 dog. The fourth person said they had 1 dog. And the fifth person said they had 2 dogs. Our frequency distribution is just how frequently each of those values occurred. So we had 1 person that had 2 dogs. We had 2 people who had 1 dog. And then we had 2 people who had 0 dogs, right? So just how frequently each of those values occurred, the 0, the 1, and the 2, is what our distribution is. Now, in this unit, what we're going to do is we're going to learn how to visually display our distribution. So the distribution, one reason why it's so abstract is it occurs whether or not we have organized it in a way that we can make sense of it. So the distribution is just how frequently each value occurs within our data set. And the different ways that we can visually display our distribution are in some things that you've probably done before. So if you've made a histogram before or a bar graph or anything like that, those are ways to show our distribution visually. So specifically in this class, we're going to focus in on learning different types of frequency distribution tables. There's a few different ones I'm going to teach you. And then we're also going to learn about the histogram, which is another way to visually display our distribution. So this is one of those terms, and we'll pause on this for a minute, but this is one of those terms, distribution, that students struggle with frequently. And if you're in my in-person class, I'd probably ask you almost every class period after we had this. So this is one of those things that you're going to want to star and that you really memorize. Remember, it's really important to memorize the key terms that I'm teaching you, the symbols that I'm teaching you, and making sure you're able to hit those unit learning objectives as well. Okay. So make sure you keep practicing this word. And if you have questions, you can ask questions in the lecture. You can also come into my office hours. All right, so there are 4 visual displays of distributions that I'm going to teach you in this class. There are more than this. So like a pie chart is a type of display of a distribution. But I'm going to only teach you 4 of them. I'm going to teach you the ungrouped frequency distribution table. I'm going to teach you how to make the cumulative frequency distribution table. I'm going to teach you to make a grouped frequency distribution table. I'm also going to teach you to properly make a histogram or histogram. All right. So the purpose of displaying these distributions visibly, it helps us to do a whole lot of things. Specifically, it helps us to see if the shape of our distribution follows the normal curve. In the future, when we move on to inferential statistics, that's going to be one of those things that you have to have with your data set before you can do some of these analyses that we're going to learn. And so in this unit, we're going to learn how to display our data in a histogram so we can visually look at it and see, does it follow the bell curve shape, which we'll learn about a little bit later in this lecture, or does it have some other type of shape? And this will help us to understand later when we're working on something a little bit more complex. So again, we're going to use this as a basis for what we'll do with inferential statistics, which we'll learn about later on in the semester. Again, this is going to help us see what the shape of our distribution looks like, which will be very, very important. And then this unit will actually help us in our next unit that will help us understand that when we see the picture of a normal curve and that we talk about normal distribution, we're talking about that there's participant data that follows that shape, right? So if in the middle, and we'll talk about this more, if most of the people fall in the middle, and then if we go to the tails of our distribution or the shape that we have over the top of our histogram bars, and there's usually very few people in the little tail. So if we look at height, human height, and typically when they do human height, they go by biological sex. And so if we're looking at height of one of the biological sexes, we'll see that a majority of the people have about the same height. There's an average height and most people fall around that. But then we have really, really, really short people and we have really, really, really tall people too. So typically if we were to graph that out on a histogram, it'd fall kind of a normal curve shape. And so if I were ever to just draw a normal curve, and which we'll keep working on as we move through the next unit as well, I want you to be able to understand that there's people's data that's underneath that. And so when in this unit, when we're making our histograms, we'll start seeing, okay, so if we have these histogram bars look at this certain way, then it has this particular shape. And then we'll be able to use that to talk about the shape of our distribution. Okay, so we're going to get started with frequency distribution tables to start off with. Okay, and frequency distribution tables, these are just tables that we make that organize a data set to display how frequently each value occurs. And you may have done this before, maybe not, but I'm going to teach you 3 different types of frequency distribution tables that you can make for this class. So the 3 types that we're going to learn, the first one that I'm going to teach you is the ungrouped frequency distribution table. The next one that I'm going to teach you is cumulative frequency distribution table. And the last one that I'm going to teach you will be the grouped frequency distribution table. All right, so let's get started with the first type that I'm going to teach you in this class. The ungrouped frequency distribution tables. Here, what we're doing is we basically will list out all the potential values from our data set from the maximum to the minimum value. And we will literally write how frequently each of those values occur in our data set. Okay, so in an ungrouped frequency distribution table, we list all of the values, even if the frequency of that value occurring in the data set is 0. We can do ungrouped frequency distribution tables for data on all levels of measurement. So earlier on in the first unit, when I said, hey, these levels of measurement aren't going away, I was not lying to you. So if you're still struggling with levels of measurement, let me know so that we can work through them because they're very, very important for almost everything that we're going to do in this class. All right, so we have steps for creating an ungrouped frequency distribution table for data that's on a nominal level of measurement. What was that again? Do not write the answer. Just pause me, think about it, verbalize it, and then come back and check your answer. If you said that nominal data is where we have numbers just represent some sort of category or some sort of phenomenon, you're right. They have no quantitative meaning. There's no order to them. We can actually make the key and make the numbers anything that we want. So we could have what's your favorite candy bar? 1 could be equal Heath bar, 2 could equal M&Ms, 3 could equal Reese's peanut butter cups, 4 could equal Snickers, 5 could equal Payday, and so forth. I could literally put that in any order I want. That's because the numbers just represent some sort of phenomenon. All right, so when we do this, we're going to create a table with 2 columns. The column on the left, we're going to name it whatever the variable name is. So for that example of candy bars, we would say candy bars. Then the right column, we will title that column frequency. Then we're going to literally list all the different types of variables and the variable column in a logical order. What do you think a logical order would mean? Most of the time, we're just going to put it in alphabetical order. So if you said alphabetical order, you are correct. So then in the frequency column, we just list all the frequencies for the options listed in the variable column. So if one person liked a Heath bar, we'd write 1. If nobody liked paydays and that was an option, we'll just put 0 as the frequency because it was still part of our list. And then the very last thing that we'll do is we'll give our ungrouped frequency distribution table a name. So if we look here, I made an example of a frequency in ungrouped frequency distribution table for nominal data. We'll see at the top, I have a name, favorite holiday, frequency distribution table. In the left column, I have favorite holiday, which is what the variable name was for it. The right column is frequency. We see that we have them listed, the holidays listed in alphabetical order, which is logical for this. And then we wrote the frequency, and even if nobody selected one of the holidays, we still wrote that it had a frequency of 0 because it was one of the options that we asked our participants. All right, so if we go and we do a frequency distribution table for ordinal data, it's similar, but instead of putting things in alphabetical order, why would we put ordinal data in kind of the order that I have here for year in college? If you said because ordinal data has an order, you are absolutely correct. So here we have first year, sophomore, junior, senior, and graduate students. So we have an order to it, so it makes sense to put them in the order. We noticed that when I did this and I asked my class what year you were, that we had 6 sophomores, 9 juniors, 6 seniors, and 0 graduate students that time. All right, so steps for creating an ungrouped frequency distribution for scale data. What was scale data again? Pause me because it's going to be important for you to know. So we're practicing. It's kind of harder for me to quiz you all online than it is for my in-person class. So when I ask a question, pause it real quick, see if you can answer my question, because that's us studying. Okay, so what is scale data? If you said it was data that was on an interval or ratio level of measurement, you're correct. Good job. All right, let's keep going. So we have steps for creating an ungrouped frequency distribution table for data that's on an interval or ratio level of measurement. Another way to say that is it's on a scale. So just like we did with our other ones with an ungrouped frequency distribution for scale data, we're going to create a table with 2 columns. Title the left column, whatever the variable name is. Title the right column frequency. List all the potential x's or the x values in the variable column and place the highest value at the top. So this is where it gets a little bit different. When we have data that's on a scale, we'll have the highest frequency or the highest maximum values at the top all the way down to the lowest value. So if I was saying, hey, let's do an ungrouped frequency distribution table for test scores. And let's say we had one person who got 100% on our test and we had one person who got a 0% on the test. We would start at the top with the variable and it would have 100. And then we'd list every single value all the way down to 0. That's actually kind of a tricky situation because we would never make an ungrouped frequency distribution table with that many rows. So that may have been not a super great example, but that's the one that we're going to use because that's what I started going with. So when we do that, that throws people off because a lot of times people don't want to put the highest frequency or not the highest frequency, but the highest maximum value X at the top. It feels counterintuitive, but to properly format your ungrouped frequency distribution table, that's what you do. Because what we're going to do is later that can help us create a different types of frequency distribution table that allows us to find percentile ranks and percentile points. All right, then in the frequency column, then we're going to list all the frequencies, even if the frequency equals 0. And then we're going to give our ungrouped frequency distribution table a name. All right, so if we look here, I created an example of an ungrouped frequency distribution table so that you all can see what I am talking about with these little tables. So we see we have our left column named height, which is our variable in inches. In the right column, we see that it's labeled frequency. We see that we have a title up at the top that says height ungrouped frequency distribution table. And then we see that we have the tallest height up at the very in row 2, but the first row of our data set. And then it goes all the way down to the minimum value of our data set, which was 63. We notice that we have all of the different types of height. We have 73, 72, 71, 70, all the way down to 63, that we didn't skip them, even if it had a frequency of 0. Okay, that's really, really important that we don't skip out on some of them, because then when we take this understanding to go and build histograms a little bit later in this lecture, that will help us determine what the shape of our data set actually looks like if we're going to visually display it in a histogram. So again, notice the largest height is at the top and the smallest height is at the bottom of the frequency distribution table. Also note that if there was not a person with a certain height, we still included all the values in the range, such as the case with the height of 72, 70, and 64 inches. All right, so now that we've done our ungrouped frequency distribution table, we can move on to doing our cumulative frequency distribution table. And our definition for this is it's a frequency distribution table that also incorporates the cumulative frequency and percentage cumulative frequency columns. All right, so basically, we're going to use the ungrouped frequency distribution tables that we already learned to do in the last bit of lecture, and we're going to kind of expand upon it. All right, so when we're talking about this, there is a phenomenon called percentile ranks and percentile points. And a cumulative frequency distribution table provides information on the percentiles for each X value in our data set. This becomes important, especially if you go into some sort of profession where they're comparing whether or not there's typical or atypical development. So for example, if you're an educator, it's really important to be able to understand percentile ranks. If you are a psychologist, if you are an athletic trainer, if you're OTPT, if you are a whole number of like career fields, I mean, medical field, like almost everything, you're going to want to be able to tell, hey, is this person's development typical or is this atypical development? And through having percentile ranks, you're able to do that. If you end up having children one day, it's really good to have the understanding of what percentile ranks are, because a lot of times when we get standardized testing or reading levels and things like that, they'll send percentile ranks home. And a lot of times parents can be confused about it a little bit because there's just, it doesn't fit with our understanding of academics a lot of time. We'll talk about that in a minute. So percentile ranks then tells us the percentage of participants that equal or fall below the associated X value in our data set. Sometimes we hear percentile ranks called percentiles, okay? Most of the time people are going to call them percentile ranks because there's something else that we're going to talk about in a minute that might be confused, but sometimes people will call us percentiles. So if you ever heard someone say, hey, I'm in the 50th percentile, that means they're average, okay? But that can be confusing because we have another phenomenon called a percentile point. And this is the X value that is associated with a certain percentile rank. So I'm going to make up an example off the spot, but let's say that on my test, I got 100, or no, let's say I got 75 points out of 100 on my test, right? So my X value is 75. And if that is the average, if that is the average score that people got, the percentile rank would actually be the 50th percentile. We will talk about the understanding of that as we move forward in this unit and in the next unit. Okay, so when we create a frequency our cumulative frequency distribution table, what we're doing is we have whatever variable we're looking at. Here I have this labeled with a row column. That is just so I can talk you through this example. It's a little bit harder because I can't draw it up on a whiteboard or anything to show you how to do this. But if we look here, we have our variable of interest. So that could be whatever variable we're studying, and those are our values. So we see that we have our maximum value at the top, which was 10, and our minimum value down at the bottom, which was 8. To the right of that, we see our frequency column, and that's just like we've been doing with our ungrouped frequency distribution table. So we have our frequencies listed. The thing that's new here is we see that we now have a cumulative frequency column as well. So what I like to do is I would like us to look at the bottom row, or row 3, and move all the way to the cumulative frequency column. And when we look at that, we see that the cumulative frequency, what it's doing is it's just adding up all the values that are at that value or down below. So if we look in row 3, the frequency for the variable interest of 8, that's just 1. There's only 1 at 8 or below, because there's nothing below it other than that. Then when we move up to row 2, we see that the cumulative frequency is everything that is of the variable of 9 and variable of 8, right? So we see that variable, the X value of 9 had 2 people who selected that. We see that 1 person selected 8. And so when we add that 2 plus that 1, we see that the cumulative frequency for row 2 is 3. And that's, so what we're doing is we're looking at the table. So for the cumulative frequency, it's taking everything that's at that value and below. Okay, and it's adding it up. So then when we go up to that row 1, we see where the X equals 10. We see the frequency for that one is 2. And so when we go to look at our cumulative frequency in that very last column, we see that we are looking at the frequencies of all the values from 10 and below. So we see that 2 plus 2 plus 1 is 5. Okay, so what it's doing, it's kind of doing like the snowball effect, kind of in some ways. So we see at the bottom, we just had that one frequency because there's nothing below it. And then what it's doing is it's collecting all the frequencies as it moves up our table. Okay, so we see that our total frequency is 5, right? There's 5 respondents to whatever survey that we're having. And then so for this percentage cumulative frequency column, which is going to be the last column of our cumulative frequency distribution table, we see that we're just seeing what percentage of our data set falls at that X and below. So we see here, if we go back to row 3, we see that 1 out of our 5 participants selected the variable 8. Okay, so when we do that, we take the cumulative frequency, which was 1, and we divide that by the total frequency, which is 5. So when we take 1 divided by 5, we see that equals 0.20, because we know we're going 2 places past the decimal. If we convert that proportion into a percentage, we see that 20% of our data set selected the value 8 or below. Okay, so then when we move up into row 2 and we're looking at the X equal to 9, we see that 3 participants selected 9 or 8. And so when we go into that percentage cumulative frequency column, we take 3, which is our cumulative frequency for that row, and divide by our total frequency, which is 5. And when we take 3 divided by 5, we get 0.60. If we convert that proportion into a percentage, we see that 60% of our data set selected an X of 9 or below. See how it's kind of cumulative and collecting like a snowball? And then when we get to our top one, when we get to our X equals 10, we see that our cumulative frequency for that was 5, right? And so we remember that our total frequency was also 5. So when we take 5 divided by 5, we get a proportion of 1.00. If we convert that proportion into a percentage, we see that 100% of our data set selected a variable of 10 or below. So what we're seeing is what percentage of our data set falls below this number. And so if we translate this into standardized tests, it could be weight, it could be height, it could be head circumference. There's so many things that can be calculated with this. If your X, whatever X you select, if 50% of the data set falls below that X you have, you see that you're average, right? 50% have done better than you, 50% have done worse than you. So if we're talking about like the ACT and you got in the 50th percentile, you're right in the middle. You're right in the average. You're where people who think they want to go to college, so they took this exam fall. All right, so let's talk about the steps for creating a cumulative frequency distribution table for scale data. First step is you're going to create a table with 4 columns. Title the left column the variable name, so whatever you're studying. So if you're doing ACT scores, if you're doing body weight, if you're doing height, and then you'll just label that. The second column to the left, you're going to label that frequency like we've been doing. The third column to the left, you're going to label cumulative frequency. Then the column on the very far right, we're going to label that one percentage cumulative frequency. Okay, so then after we do that, we're going to list all potential X values in the variable column from the maximum to the minimum values. In the frequency column, we're going to list all the frequencies for the X values that are listed in our variable column. Even if their frequency is 0, you still have to have that as a row on your frequency distribution table, this cumulative one. Then in the cumulative frequency column, start in the bottom row and add up all of the frequencies from that row's frequency through the bottom of the table. Remember, we're just collecting them as they move up. Then I want you to find the percentage cumulative frequency for each row. Remember, we do that by taking the cumulative frequency divided by the total frequency of the data set. And then you have to give it a name. So that's a big thing to not forget. We want to name that cumulative frequency distribution table as well. All right, so that moves us on to our group frequency distribution table. And these types of distribution tables use groups, in other words, something called class intervals, to cover a large span of variables to reduce the number of rows in the frequency distribution table. All right, so there's going to be some terminology that we need to learn for this that can be confusing. So you're going to want to memorize these terms. So if you're making flashcards for this class, go ahead and write those down. Do that now while we're going through the lecture. That is one way to make sure that you're evenly studying for our exams and that you're pacing yourself so that you can really understand this information. So our first terminology that we're going to learn are class intervals. And these are just the different ranges of data used in the rows of a group frequency distribution table. When we actually go through and I start showing you some examples of this, this will make a lot more sense for you. But this is just our little groupings that we're doing. So in the previous slides, when I was saying, hey, if I had this exam and we had someone get 100 out of 100, and then we had someone get 0 out of 100 on it, we'd actually probably create a group frequency distribution table for this because we don't want to have 101 different rows. And you're like, but you said it's from 0 to 100. Why would there be 101 rows for the different variables, right? It would be 102 if we add the headers at the top. And that's because 0 is also one of those rows, right? So this is one reason why it's actually super important to learn about the inclusive range earlier on is actually this unit here, because we have to make sure that we're accounting for all of the information that we're doing in this set. Something else that I want to teach you about is called class interval width. And we have a symbol that you should put onto your handy dandy symbol sheet. So lowercase italicized I is our symbol for class interval width. And this is just the inclusive range of each of these class intervals. So the class intervals are the actual groups. So if we have that other example where I had 0 up to 100, we'd likely have different class intervals. We'd probably have 0 to 9, 10 to 19, 20 to 29. Those are class intervals. And then the class interval width would be the inclusive range of each of those class intervals. So the inclusive range of a class interval of 0 to 9 would be 9 minus 0 plus 1, right? So 9 minus 0 is 9, plus 1 is 10. So our class interval width in that example would be 10. So other terminology that we'll see here, we'll also see this later when we talk about probability, but mutually exclusive. So when we talk about mutually exclusive, the way that we're going to define this for this unit is one or the other. Okay, and these will be really important terms for us to remember while we move through this unit. All right, so there's going to be tons of rules. I'm going to give you these rules, and then you're going to use them to problem solve how to create a properly formatted histogram. Okay, so for example, one rule that you have to have is that when we create these class intervals, that the class intervals have to have a consistent, so it has to be the same for every class interval that's in the one group frequency distribution table. It has to be consistent, it has to be the same, and it has to be practical. Okay, so practical would be something like two, at least in our culture, this might be different in different cultures, but in our culture here in America, 2 is good because it's the even number. 5, 10, 20, 25, 100, 1000. Something that would not be practical would be a class interval width of 13. We don't tend to think of numbers in 13s. In the math system that we use, we typically think of even numbers. We think of 10s. 5's okay if you need to do it because you can make 5 into 10, 5, 10, 15, 20. And our brains typically work that way. 3 would not be a good class interval width because that gets really messy when you're moving through and creating these. Okay, so another rule is the first number of the lowest class interval. So if you remember, we put our highest values at the top, lowest values at the bottom. The first number of our class interval must be a multiple of that class interval width. So if I was talking about, if I had a data set that ranged from 20 up to 50, right? My first class interval would have to start with the multiple of whatever that class interval width is. So I know this is an example and the math might not work out, so don't hold me to this, but if we say like we had a class interval width of 5 and 20 would be okay starting out our class interval because 20 is a multiple of 5. So it's likely that that class interval would be 20 to 24. Then we have 25 to 29, 30 to 34, 35 to 39, and so forth. If that ended up working out after I teach you all these rules. All right, so then the lowest class interval has to contain the lowest value in the data set. So let's say with that same example, say our lowest value was not 20. Say like our lowest value actually was 21. Well, 21 is likely not going to be the first number of class interval because that's not going to likely be a multiple of our class interval width. So for the example that I just did, say like 21 was our lowest data set, but we still had everything else the same. Our first class interval would probably still be 20 to 24, and that 21 is subsumed within that group, so it's okay, but you have to make sure that you do have some sort of frequency that's in that lowest class interval. When we start seeing some examples as I move further along in this lecture, you'll be able to see what that means a little bit more. Each of our class intervals also have to be mutually exclusive. So what this means, if you remember from the previous slide, mutually exclusive means one or the other. This means that when we're creating these class intervals, we can't do a class interval of 20 to 25 and 25 to 30 and 30 to 35, because what we see there, if we have any x's that are 25, that would fall in 20 to 25 and 25 to 30. Each data point can only be represented in one of the class intervals that we have in these tables. Okay, so again, mutually exclusive means that each value in your data set can only fall into one class interval. And students, sometimes this messes with their heads because we do like even numbers, right? So remember with our class intervals, the very first number is going to be a multiple of our class interval width, but it messes people up when we have a class interval of 20 to 24 because they want to make that last number a pretty number also that follows the same rules. But we know that with a class interval width of 5, right? That's the inclusive range of our class interval. And so we see 24 minus 20 plus 1, right? So 24 minus 20 is 4, plus 1 is 5, which is our class interval width. Okay, so steps to creating class intervals. There's a little bit of a trick. Nobody taught me how to do this. This is something that I kind of developed on my own for how to kind of problem solve how to create our class intervals because it's a little bit tricky. Okay, so I say first find the inclusive range of the entire data set. Then using that inclusive range, you have to determine what class interval width makes the most sense and will result in 10 to 20 class intervals. So when we're creating our distribution table for this, we have to make sure that we have 10 to 20 class intervals. So that means that with data, there'll be 10 to 20 rows with class intervals in them. Okay, again, you got to make sure the bottom class interval contains the lowest value in the data set, and the very first number needs to be a multiple of that class interval width. Okay, so we have an example here. We see here, how good is your day from a scale of 0 to 100? We see I have this data set here. So participant ID, again, those numbers just tell us that that represents some participant. Each of these people have a name, but we do that to keep the identity of our participants safe. So 0 represents the worst day ever, 100 being the best day ever. And I literally asked people this question. They responded so that we could use this data set. And we looked that there's some variability in here. So let's practice finding the class intervals for this data set. If you remember, I said the very first thing that we should do, and make sure you're writing this in your notes. Make sure you're going through these because stats is a really, really hard class. And I think it's really, really difficult to take online. It's definitely difficult to teach online for sure, because it's harder for me to check your understanding and things. But make sure you're doing these activities with me, because if you don't follow along and actually do them in your notes, it's going to be really, really hard for you to take exams in this class, because I actually am more interested in your understanding and critical thinking than I am actually in the math. But in order to understand what we're doing, you still have to work through the math to do that. So we look here. If you remember, we said, let's take the inclusive range of our data set was the first step. So in there, how do we find our inclusive range? So to find our inclusive range, we have to find the maximum value in our data set, and then we have to subtract our minimum value in our data set from that, and then we have to add 1 to it, and that will get us our inclusive range. Okay, so again, practice doing this in your notes. And then when everyone in our online class is done, I'm joking, you don't have to wait for everyone. We don't actually know when people are finishing these things. We'll check and see how you did on our next slide. Okay, so you do that. So after you get that inclusive range, actually, let's talk through it. What's our max value here? So I'm looking through the data set. Okay, so I think the max value in here is 85. It's not like my in-person class where you can correct me if I'm wrong. So hopefully I'm right here. I'll check myself on the next slide, just like you will. So I think our X max value, and I'm writing this down on some paper, I believe that's 85. I believe our X minimum value, let's look through here and see what our lowest one is. Wow, someone had a really bad day. I think our minimum value is going to be 18. So here, if I want to find a inclusive range, if I'm right on these values, I'm going to take 85 minus 18 plus 1. So go ahead and do that. I'm going to break out my calculator right now and do this right here with you all. All right, so on my calculator, I got 68. And so now what we do, if we want to try to find a class interval width that will result in 10 to 20 class intervals, what would you do to try to figure that out? Remembering our inclusive range of our data set is 68. What would you do to try to figure out what range our class interval width should fall in if we want 10 to 20 class intervals? Pause me, think about it, struggle a little bit if you need to, and then come back to me. All right, so one way I do it, because we know that we want like 10 to 20 groups in our group frequency distribution table, I like to take my inclusive range and divide it by 10 and get a number, and then take my inclusive range for our data set and divide it by 20. So go ahead and do that now if you haven't already. So take 68 and divide it by 10 and find that answer. Okay, you can use a calculator if you want. And then after you do that, you can do 68 divided by 20. So I'm gonna double check myself real quick because I don't have y'all right here with me to double check my answer. So here what I have is when I took 68 divided by 10, I got 6.80. When I divided 68 by 20, I got 3.40. And so when I'm thinking about trying to find an appropriate class interval, typically what I'm going to try to do is look between these numbers. So our class interval width, I misspoke for a minute there. So when I'm trying to find it, our class interval width should fall somewhere probably between 3.40 and 6.80, right? So this is the math I did on a little sticky note. I don't know if it's going to let you see it very good. I had a little calculation error. It's okay. I told you all to do your math in pencil, not with a pen. So I didn't even listen to my own advice. And so I made a mistake. I jinxed myself. So what is a good practical number that falls between 3.40 and 6.80? If you said 5, I would agree. I think our class interval width, we could try 5 to see if that results in us having 10 to 20 frequency or a class interval. So we look here and I went ahead and created this group frequency distribution table. Actually, you should probably try to do the same. So go ahead and try to make yours as well, if you can, but I've already shown you, so I'm going to flip over to the next one anyway. Go ahead and pause me if you need to build it. We see here, we have how you doing, right? I was being cute. That's our variable. We see that the class intervals, I told you, like when we see it, it might be a little bit easier to understand. So 85 to 89 is a class interval, 80 to 84 is a class interval, 75 to 79 is a class interval, 70 to 74 is a class interval, and so forth. So when we see this, we have the different class intervals, and we want to make sure we have 10 to 20 of these. So let's count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes, so we have 10 to 20. We see that we kept a consistent class interval width. Remember, our symbol for class interval width is I, lowercase italicized I. Because if we take 19 minus 15 plus 1, so we take 19 minus 15, which is 4, plus 1 equals 5. And if we did that for each of our class intervals in here, all of them, we'd see that all of them have the same class interval width. We'll see, so we have our variable in our left column, we have our frequencies in our right column, and we have them even for our class intervals that don't have any frequency. It's really important to include that still as we move through it. And then we see that we gave our group frequency distribution table a name. Okay, so it's really important to have all of those properly formatted. All right, so that moves us on to histograms. It's likely that you've been familiar with histograms before. Something that's really important, though, is I'm going to teach you some formatting rules, because although you've been presented probably with histograms and other types of visual displays of data in the past, sometimes people will not format them correctly so that they can try to push their own agenda with data rather than letting data speak for itself. All right, so histogram. This is a diagram that visually displays the distribution of a data set. The histogram uses bars to indicate how frequently the different values in the data set occur. Okay, so the histogram uses bars to show how frequently the different values in a data set occur. So it's literally visually displaying that distribution that we talked about earlier on in this unit. Because even though the distribution always exists, whether or not you display it, that's a hard thing for us as concrete animals to be able to really understand. So histograms are really great because I think even more so than frequency distribution tables, it really shows us that our data, our distribution has a shape to it. So there's going to be some histogram basics that we need to learn. To continue, some of this will be review. So when we're creating a histogram, our x-axis is our horizontal axis of the histogram, which typically displays the class intervals or the ungrouped values of x. So you can actually create histograms for grouped or ungrouped data. Our y-axis then is the vertical axis of the histogram, which usually displays the frequency of the class intervals or ungrouped values of x. The origin is the point where the x-axis and y-axis meet. it always equals 0 unless it's identified otherwise on the histogram. So if it doesn't equal 0, then someone needs to write what it actually is. Almost all the time, we're going to have that there, though. All right, so here you'll see I have a picture of a break in our axis. And we do that when we see that there's going to be a long jump between 0 and our first class interval. Okay, so often there is a significant gap between 0 and the first class interval, and we'll use that break in the axis, which kind of looks like an EKG a little bit. That tells us that we're jumping to our class intervals. So again, to indicate this on a histogram, create a break in the axis. Again, this kind of looks like EKG output. All right, so something else we need to learn are about midpoints or review maybe for some people. So when we are creating histograms, we actually use the class interval midpoints to identify the class interval. So on our x-axis, you might be tempted to write out the full class interval. So if we had like 0 to 4, 5 to 9, so forth, but you wouldn't do that. We actually use the midpoint of each of those class intervals to identify which one it is. And this messes people up. I didn't make this rule. This is just a formatting rule to make a proper histogram. So again, we do not write the class intervals themselves. There's something you can do that I'll teach you that if that kind of messes you up so you can keep track of what's where. But along that x-axis, we'll be using the midpoints to identify our class intervals. So it might have been a while since we've done midpoints. And when we do midpoints, what we're doing is we're trying to find what the very middle of it is. So if we wanted to find the midpoint of the class interval of 1 to 4, what would we do? If you said we would find the mean of those two numbers, you're absolutely correct. So to do that, to find the midpoint, we'd take the mean of the maximum and minimum values of each of our class intervals. So for this example, go ahead and try that. All right. So when we do that, we find that our midpoint for this would be 1 plus 4. And we do that first and then divide that number by 2. So we have 5 divided by 2. So we find the class interval midpoint is 2.50. So if we were creating a histogram and we had a class interval 1 to 4, which we would never do because that is a class interval with a 4. But if we were doing this per se, we would use 2.50 to represent the middle of that class interval, and that would be what would be along our x-axis. We would not write 1 to 4. All right, so histogram creation steps. Okay, you got to create, if it's necessary for you to have class intervals and you're not using ungrouped data, you would need to create a practical and consistent class interval width to properly create class intervals for the entire data set. That's what we did with our group frequency distribution table. You do the same steps for that to problem solve that. You draw the x-axis and y-axis and make the y-axis 3/4 the size of the x-axis. That confuses students sometimes. Let me show a little picture. I'm going to estimate. So if we're looking at this, our x-axis is going to be longer than our y-axis. This should only be about 3/4 as tall as this is long. Okay. And so when we do that, our histogram should take on the shape of a rectangle. And so if you ever see a histogram out there where it looks like a square, that's not properly formatted, and that's not going to tell you the correct story of what the distribution looks like. So it's really important that we follow these formatting steps so that we can get a really good idea of what our distribution looks like if we visualize it. You're going to label the origin 0 unless that's not true. The x-axis, you're going to list the name of the variable. So with our other one, what was our variable called? It's called how you doing, right? So we'll write how you doing on the bottom. And then our y-axis then will be the frequency. Then if there is a huge jump from 0 to your first class interval, you're going to make it that break in the axis that looks like the EKG output. And then you're going to write in the numbers for the frequency along the y-axis. And then you're going to put the midpoints along the class for the class intervals along that x-axis. And then you're going to draw bars to represent the frequencies of each of the class intervals. So there are some optional steps that I told you that you could do if some of these things really bother you that are not against formatting, but might help make things more clear for you. Because many people dislike the use of midpoints along the x-axis. Some people opt to put the range of each class interval within the bars of the histograms. That's optional. So literally with the one example, we had 1 to 4, you would have your bar and you'd literally 1-4 inside the histogram bar. You don't have to do that. It is not necessary to have a properly formatted histogram, but some people like to do that, especially in this class while they're learning, so that they remember what those midpoints are. Also, some people like to write the frequency number at the top of the histogram bars. That's also not something you have to do, but some people like to do that to help them out so that they remember that's what it's telling them, that it's the frequencies. Okay, so let's do a summary real quick. Histograms their bars are gonna touch. You're not gonna have any gaps. The only reason we would have a gap was if there was a frequency of 0 in your histogram, and so then there wouldn't be a bar there, so that would naturally put a gap there. But if each of the groups or each of the values have frequencies, those bars are going to touch one another. There's going to be no space. You're going to leave that space out. Okay, again, we're going to use the midpoints of class intervals to identify the class intervals instead of the ranges. You're going to develop the class intervals and class interval width the same way you did for the group frequency distribution table. You're going to include one class interval lower than the class interval containing the lowest value of your data set. So this is a little bit different formatting rules from when we did our frequency distribution tables. What this means is that if there is that big jump between 0 and then you do that break in the axis, you're going to have one class interval that has no data, and then the very next one will be the one where your frequency starts. So what that does is it helps orient you so that it has more space to look nice. All right. Again, you're going to make that y-axis 3/4 the size of your x-axis. Okay. Here's a checklist. I am not going to, maybe I should go through this. You don't have to write all this down. But when we get to the point where you're building a histogram for me, you're going to want to go through and make sure that you're checking all of these things, because these are the things I'm going to look at when I'm grading. So does the histogram have a title? That's an easy point. Is the I can talk, right? Does the x-axis, is it labeled? Is your y-axis labeled? Is there a break in the axis if there's a jump from the origin to the first class interval? And the histogram, if necessary, did you include one class interval below the first class interval of the data set? Do the bars of the histogram touch? Is the frequency written along the y-axis, right? Are the values of interest along the x-axis? Are the class intervals mutually exclusive? Is the class interval with a practical value? Are there 10 to 20 class intervals if you're using class intervals? Are the midpoints along the x-axis used to identify the class intervals? Do the bars of the histogram align to the proper frequency that we have? And then is the y-axis 3/4 the size of the x-axis? So these are things that you're going to want to check while you're building them. You know, a lot of times, actually, you're not going to have to build these by hand. For this class, I like to do that just because that helps us give an idea of what this information really means. But eventually, when you move beyond this class and you're out using this in the real world, you'll use some sort of computer program to do this for you. But the reason why it's so important for us to do it like this is so that we can tell when someone's trying to fabricate data or try to make data tell a story it's not supposed to be telling. So build a histogram workshop. Now I want you to practice this. So pause this video, get out your notes that you should be taking some notes on, and use this data set and build yourself a histogram. So what I want you to do is pause me right now. I have a template histogram that you can print off, a PDF of one in our module materials, or you can just build one in your notes, right? I would suggest using a fresh sheet of paper. People tend to struggle with making histograms, even if it's something that you've done before. And so you're going to want to do this in pencil most likely, because people really actually struggle with building histograms. So that'll give you a chance to practice. All right, so pause me and go ahead and do this. All right, so again, we want to create that histogram for how good is your data set from a scale of 0 to 100. You can use the class intervals we created for the group frequency distribution table because this is the same data set. So again, do this now and ask me questions as necessary. You can do that by writing questions in the lecture. You can also come into my office hours for help, but make sure you can do this correctly on your own. Pro tip, and I already told you this pro tip, use a pencil to create the histogram because you will be erasing as you learn to do this. You will. All right, so here is my how you doing histogram. We can look here. I have my frequency along the y-axis. I have my variable, how good day it was, along my x-axis. You see that I use the midpoints of each of the class intervals to identify the class interval. So the midpoint is identifying which ones it belongs to. You'll see that the origin is labeled as 0. I have a title. You will also see that my bars are touching where I have frequencies. If there's a frequency missing, then it obviously just doesn't have a bar there. We see that I have one class interval before where my data set begins. Something else that I didn't talk about earlier, you'll notice that my bars, sometimes students struggle with that. My bars are straddling those midpoints, right? So if we see with the first class interval that has data in it, that bar has the midpoint in the very middle. And that's because if we think about what this represents, we have it right in the middle of our class interval. We have an X minimum value, which is to the left of our midpoint, right? And then we have an X maximum value that's to the right of it. So this is what your data set should look like when you graph it as a histogram. And we see that we could actually kind of get a shape if we drew over the tops of our histogram bar. And I might have a function in here. Let me see if I have a function where I can draw on here. Let's annotate this real quick. Yes, I do. So if we look here, we can actually kind of, and that's really ugly. It's really hard to control this. But if we go over the top of these histogram bars, we kind of have a shape. And that was really, really hard for me to control while I'm trying to draw over it. But that's what we're talking about when we say we can see the shape of our distribution if we put it into a histogram. And that'll be really important to remember as we move forward in this unit. All right, so discussion. How could people manipulate histograms to support their own thoughts and ideas? So think about this. We can discuss this. You can write a discussion if you want, or you don't have to. That's not required. That's just in case you're craving that class interaction or faculty interaction. But think about this. Come up with an idea. So if we go back, I'm going to flip back onto our histogram. If I were to make my y-axis taller, it would actually make it look like there's not so much of a difference between my different bars, right? It would make the frequencies look like they're closer together. And conversely, if I shorten my x-axis and I move it in and make it come in like this, that would make it look like there's huge difference between the frequencies that might not actually exist. So these are some things to keep in mind while building these. It's really important to have that y-axis be 3/4 the size of our x-axis, because that helps us keep the proportions the same. And as long as we keep building histograms this way, then our brains start to interpret it in a better way. Okay. So there are different shapes of these distributions. And if we build histograms, it's easier to see what those shapes are. Some common shapes of distributions include the normal distribution, the J-shaped distribution, the rectangular shaped distribution, the U-shaped distribution, and the bimodal distribution. So the normal distribution is the one that we're going to use the most. And we see here with the normal distribution, it refers to a group of distributions where most of our sample is going to fall in the middle and extreme scores fall to the far left and right. And so, and I have an annotation tool. So I struggled last time with making this work, but we're going to try it again. And I'm going to draw. There is a reason why I am not your art teacher. But something you have to remember, a lot of times when we're looking at the normal distribution, when we move on to the normal curve in the next unit, we're just going to see this curve. We're not actually going to see the histogram bars. Like there are actually, if we remember, there are participants' data that fall underneath this, okay? And that's kind of ugly. And we're going to erase that, because the big thing that I want you to remember when we're doing this, and I'll draw it, is that we have people's data under here. There's literally people's data under here. There's lots of people, right? So earlier when we were talking about how, like, most people fall within a certain range for their height. There's like a normal typical range for their height based on their biological sex. But there's very few really, really short people, right? And there's very few really, really, really tall people. I could draw little stick figures under here all day. We'll just be obnoxious and draw a bunch of them. But the thing that I want you to remember is that anytime that we see that normal distribution or the normal curve, that there's actual people's data, like there could be a histogram underneath it to represent all of it. So let's just do this undo button, or I can clear it. There you go. I will learn to use this more effectively for you all. All right, so we also see a J-shaped distribution. Remember, whenever we draw the shape, this is over the tops of our histogram bars. And this is when the data set's distribution on histogram looks like it's a letter J that's laying on its back, or a mirrored image of a J laying on its back. Okay, so we have a high peak at one of the edges of the histogram because most of the participants selected one option, and the rest of the options have relatively low frequencies. And so when we're working with data sets, when we move on to work with inferential statistics, if we have a data set that has this type of distribution, that's going to be really problematic for us for the types of stats that I'm going to teach you. There are other things that you can do, but those things go well beyond what we would do in this class. We also have a rectangular shape distribution. So we see here that I actually included a picture that had the bars on it, but if we go and we actually go draw over the top of the bars, that's really sad. We see that has a rectangular shape. If we do that, so that's where it's get its name. So another name for this is also known as, or AKA, a uniform distribution. And that's because every single value happens to have the same frequency in the distribution. That doesn't happen frequently in a lot of things that I use practically. But if for some reason every option had the same amount of participants, it would be a rectangular shape distribution or a uniform distribution. We also have a U-shaped distribution here. I found an image that has bars and kind of drew the shape over the top. And this is where we see large frequencies on both of the edges of the distribution and very low frequencies in the middle. If we drew a line over the tops of the histogram bars, it would look like a big U. So it kind of looks kind of funny there, but we get the idea. It kind of looks like a U shape. We also have a bimodal distribution. I like to think of a camel. When I think about this is because when we have a bimodal distribution, what did the word bimodal mean? If you remember from earlier on in the semester, it means that our data set has two modes, right? And so when we look at a frequency distribution table, the tallest bar of our frequency distribution table is also the what? It's the mode, right? So the most frequent values are mode. When we have a bimodal distribution like this, we have two modes. Okay. So this distribution has two modes. A lot of times, interesting enough to me, maybe not to you all, when I teach in-person statistics classes, a lot of times I see a normal distribution. When I teach online statistics, often I see a bimodal distribution where I'll see a lot of people with B's, right, with the mode. And then we'll see a lower drop in C's, and then we'll see a ton of people with D's. And it's really interesting. And like my explanation, or what I think is happening there, is that when it's online classes, I have control. I can put lectures out there. It can be the same me. I can tell students to do the same things, have the same types of assignments, same types of exams and things like that. But I can't really check in if you're doing things every day as much as I can with an in-person class. Like I take attendance in my in-person classes, right? And I do have where you get points for these lectures and you're supposed to be watching it, but I don't really know if you're actually watching it. Hopefully the Perusall software, any software that I'm using to track it will track it for you, but it doesn't mean there's not a way for you to get around that. And that's really problematic because this class is so hard. And so what I see with this class then is that students who do really well and are very self-directed, very good with computers and asking questions if they have help, being able to not procrastinate, do really well in the class. And the students who struggle with it and maybe took this online because they thought it would be easier, which is never true. I think online classes are always going to be harder. That's just my preference. We see them struggle a lot more. And so instead of seeing that beautiful normal curve like I do in my face-to-face version of this class, a lot of times I'll see a bimodal distribution of that data. And we can look at that. We can look at that later in the semester if we want. We can wait for us to get like an exam under our belt, and we could actually do this with our data, which is kind of fun. So it has two humps like a camel. So it measures the shape, which was the purpose of this unit. We have two different ones that we're going to learn about. We're going to learn about skewness. We're also going to learn about something called kurtosis. So skewness tells us how lopsided or how symmetrical our distribution is. Okay, so if our skew equals 0, then our distribution is perfectly symmetrical. And I'm actually not going to teach you how to calculate skew because a lot of times what you're going to see is most people are going to just graph a histogram so that they can see if their distribution is skewed, or they're going to do something else that checks skewness and kurtosis at the same time later on when they're going and doing different types of analyses. So the two types of skew include positive skew and negative skew. These things are just things that you're going to have to memorize, and people kind of struggle with it. So if we have no skew, this is what it looks like. That's that normal curve again that shows normally distributed data. And then we have negative skew and we have positive skew. The way that I like to think about it, because these things can be really hard. Like I said, you just have to memorize it. When I'm thinking about skew, what I'm thinking about is what part of the distribution mess things up, right? Because ideally we want that normal distribution. And if we look at a number line, typically we have our smaller values on the left side. So when we're looking at negative skew, here we see that the side that's messing it up is the tail that is on the left, which is near the more negative numbers, right? Because if we go past the origin, we get into negative numbers. And so if we look on the positive skew, we see that the long tail of our distribution is on the right side where our more positive numbers are. That's a mnemonic that I use to remember it. And I don't know if you all have ones that you can help your classmates with. But yeah, if you have some ideas about how to memorize some of these things, definitely share them with the class because that will be helpful for everyone. All right, so critical thinking. And for this, it's really good to kind of come up, like I like to draw this out. I'm going to get another little sticky note because I don't have a huge notebook in here today. But what happens to the shape of a distribution when the mean is bigger than the median, which is bigger than the mode? So to do that, you could literally pick any numbers you want. You can draw yourself a little histogram. Let me put this up here close to you. You can draw yourself a histogram. I'm throwing things now in my office by myself. Remember that the y-axis is our frequency, right? So you can write out frequency there. Our x-axis is whatever variable we're using. Let's say number of cats. Okay, so if our mean, if we think back to our unit over measures of central tendency, which one of ours, is it the mean, median, or mode? Which one of those is most influenced by outliers? If you don't remember, pause me and actually go back and review it. Go back to the measures of central tendency unit where we started talking about this, where we did the example with the number of times, I think it was the number of times people went to the zoo. Okay, so pause me, and then once you answer it, then unpause me. If you said that the mean is the one that is most influenced by outliers, you're correct, right? So if we have an outlier, it's going to pull that mean toward it. The median is always just kind of the very center of your data set, right? And then our mode if you remember on our histogram, our mode is going to be whichever one has the most frequent. So it's going to be our tallest little thing. So let's say our mean, say that our mean, I should write this down, X bar is bigger than our median and bigger than our mode. So our mode's the smallest. Remember, our frequency is going to be on our y-axis. So we're going to have frequency 1, 2, 3, 4, 5, number of cats, 1, 2, 3, 4. And then, so if our mean's going to be biggest, I got them mixed up when I got excited and started doing an example. Our mean, again, is the one that's most heavily influenced by outliers, right? So let's say that our mean of our data set is that people have 2 cats. Or our mean of our data set is they have 4 cats with our mean, with the frequency being 2. Sorry about that. I am struggling. And then our median is always going to be the middle of our data set. So let's say that 3 people have 2 cats. And then here our mode, let's say our mode is that 5 people had 1 cat. Okay, so there we go. This is the properly formatted one. And if we look here, we see that our mean, our 4 is bigger than our median, which is 2 cats. And our median is bigger than our mode, which is 1 cat. And so when we go and draw a shape over, or the kind of draw a line over our distribution shape, we see that the tail over here is over on the positive side. So we're going to have positive skew. And that's a better picture that I have for it. So if we flip that around, what happens to the shape of the distribution when the mean is smaller than the median, which is smaller than the mode? Okay, so if we draw an example, drawing our little histogram out. Remember, our frequency is on our y-axis. Okay, let's say this one's number of dogs, example. None of this is real. This is just so that we can see what happens when our mean, median, and mode don't line up. So if our mean is the smallest thing, right? So if our mean has the smallest number, that means our mean is going to be drawn out likely because we have some sort of outlier that's on this side. So if our mean is here, let's say that 2 people have 2 dogs. Let's say our median, which is always going to be in the middle. Let's say that 3 people have 3 dogs. I am making this outlandish right now. And let's say our mode is that 5 people have 4 dogs. So when we see that our mean is smaller than our median, and our median smaller than our mode, it takes on kind of some of that shape. And then when we draw a line over the tops of our histogram bar, we see that that has negative skew. Okay, and that's what it looks like with a better graphic that I was able to find online. Okay, so then what happens when our mean equals our median and our mode? So think about what we did. We don't actually have to try to work it out. What happens when our mean equals our median or our mode? Remember, the median is the exact center. The mode is the tallest. The mean is the one that's most influenced by outliers, right? Pulled either way. So what happens to the distribution shape when they equal each other? Our data set is normally distributed. We actually want that to happen. Okay, so we can move on to kurtosis, which is our last measure of shape that we're going to learn in this unit. And we have 3 different types that we're going to learn. But kurtosis, if we're going to define it as a term, refers to the degree of how peaked a graph distribution is. Or another way to say it's looking at our distribution shape and seeing how pointy it is or how flat it is. And so we have 3 different types of this. I have a mnemonic for this as well. So if we have a platykurtic distribution, that means our distribution shape is flatter than the normal distribution. I like, and I don't know how many of y'all got to watch this show, but they're with Perry the platypus in it, and I think the show is called Phineas and Ferb. And a platypus, so like I imagine the platypus bill is flat, and so in my head, the way that I remember that platykurtic means that it's flatter than the normal distribution is that platypus bill. Okay. Please don't get that one wrong. I once had a student forget what it was, and they drew me Perry the platypus on their test, and it made my day, even though they got the question wrong. Mesokurtic then means that our distribution has the same peakedness as the normal distribution. So it follows that kind of normal curve shape that we'll learn about. And then leptokurtic means it's more pointy or more peaked than a normal distribution. So you should be able, if I gave you a picture, you should be able to tell me if it was platykurtic, mesokurtic, or leptokurtic. If we go back to skew, you should be able to tell me if it is positively skewed or negatively skewed, or if it has no skew. Just from eyeballing these distributions. These things will become really important as we learn about how to do some inferential statistics later on. We actually will have to look at our data before we move forward with it. So if you have any questions, please let me know. Please feel free to write questions for your classmates, for me, and then continue to work together as a community, a learning community, as we work through Stats Online. Also, feel free always to come into my office hours. I will be here. Awesome. Thanks.